Now, can we put all this together? Can we put together the Q of our the Q that we've been working with, and can we put it together with our W? Why, yes, we can. Of course we can, because quite often systems are not just one or the other. Very often you're looking at possibly a change in volume, a change in pressure that creates some sort of an energetic shift, and coupled with that will be some sort of a change in heat energy as well. So now we're starting to look more closely at the processes that get us our values. And so when you're considering both of these in a system, you're really gathering more data as a result. So in a system, we're going to say that the energy change is defined as that delta E, and it can be equal to the change in the energy of the system. I feel like I just really butchered that, but I hate to re-record it. So, but this is actually, this slide makes it, I think is what it is. This slide makes this concept more difficult than it really is. It's really not that difficult. It's just expanding how we're measuring systems to now include more than one factor. And we're going to call it the delta E of our system. So you know when you're looking at the yogurt and you're starting to count those calories and you see that you have yogurt that maybe has 150 calories in it. Have you wondered how they figure out those calories? Well, in order to get the amount of calories that food has in it, what they do is they put it in something known as a bomb calorimeter. And the way a bomb calorimeter is set up is this. You have this container, this contraption here, and it has water in it. This is water. And inside you have this little inner chamber, and they put a certain sample of your food down here. And then they have these ignition wires that come out here. And the ignition wires, once they're triggered, will send us basically something analogous to a spark. It's going to set this food on fire. And the food will produce heat as it burns, and that burn will produce heat that will heat up the water. And here we have a thermometer that is going to measure the temperature change in the water. So there is a relationship between the heat capacity of the calorimeter and the amount of heat absorbed by it versus the amount of heat that is given off by food that is burned. So that's how they figure out how many calories something has in it. So that's how they've come up with that. And remember, the calorie, the big C, is the value in kilocalories. So they figure out what the regular calorie is, the little c calorie, and then they divide it by 1,000. So you don't choke when you're eating your yogurt. 150,000 calories? No. It's 150 kilocalories. It's cool, man. And we're not even going to include kilo. We're just going to put the big C there. So we can fool you, unaware shopper. So I'm gonna just touch on 9.5, and I'm gonna go rather quickly because the concepts are basically the same as what we were talking about when dealing with the specific heat and mass and change in temperature, and that's basically what a bomb calorimeter is utilizing to get to the delta E. So if we read this, we're given grams of sucrose, which is a type of a sugar, and it's going to undergo combustion in the calorimeter, and it's going to raise the temperature from 24.92 to 28.33, so there's our delta T. And they want us to find the change in energy of the reaction for the combustion of the sucrose. Look at this, this is really important right here, these units, kilojoules per mole. So what this is telling us then is that when we're looking at the delta E of a reaction, this is not just a number based upon the amount of stuff that we were given, which is basically what Q is, but we have to go back and break it down per mole of substance. So we are given grams, and they want us to bring in the mole. What do we know that correlates grams and moles? Hopefully you're saying, why, that would be molar mass, Dr. Oliver. And indeed it would. So we're going to have to use molar mass with this problem. So, oh yeah, and also the heat capacity of the bomb calorimeter is given to us right here. So these are our given values. This is everything that I just pointed out. And they want us to find the delta E. And we are going to be using, first of all, to find the heat that was evolved by setting things off in the calorimeter. So we're going to find the Q of the calorimeter. We're going to find the Q of the calorimeter by using the change in our temperature, the amount of stuff that was burned, and the specific heat of the calorimeter. That part's going to be easy. So we are going to use this equation, but then once we find this equation, we're going to have to come up with the Q of the reaction. The Q of the reaction is going to be the opposite of the Q of the calorimeter, because we're talking about the heat that was evolved from the stuff, and we're taking it back to the stuff because we're looking at moles of stuff. I hope you really like that technical explanation. So when we use this equation, I'll go over it one more time. When we use this equation, we're figuring out the heat that the calorimeter, it's heat that went through an evolutionary process, and the heat of our sucrose will be the opposite of that because our calorimeter will absorb the heat. Our sucrose will be the one that gives it off. So its value is going to be the opposite of whatever the calorimeter is. And then we need to take that Q and put it over the moles of sucrose, like a mole of sucrose, in order to get the amount of energy of reaction per mole. So it's this last little nugget right here that makes this equation different. And the reason why you include the mole is because of how energy is defined. Energy is defined not just as like some loose number, because what if we had had a different amount of sucrose that we burned in there? Within our delta E would be different. But just like when it takes more heat to heat up 100 grams of water than it takes to heat up 200 grams of water. But we can figure out an equivalence if we knew the moles of water. If we knew the mole of water, then we could actually come up with the delta E of that reaction, and it would just be the Q of water over the moles of water. So that's what's different about this equation. I'm not going to go through the whole thing, but I wanted to explain why you had to put Q over moles in this equation. And it's because the heat, that's the change of heat per mole, and that's the way that gets measured. Now, enthalpy is another way of quantifying a system, and this is the heat that is evolved at a constant pressure, when a system is under a constant pressure. And here is the equation for that. We would say that heat is equal to the energy of a system plus the PV work that is done, provided that the pressure remains the same. Now, this may sound fairly complicated, and if we were looking at more complicated systems, I suppose it would be. But the way that we're going to apply this is that we're going to apply this in the production of products from reactants in a chemical reaction at a constant pressure and with no involvement of volume. So for us, the equation gets very simple, and we would say that the delta heat of a reaction is pretty much going to be equal to the Q of the reaction as long as that constant, the pressure is constant over the course of the reactions. So it sounds complicated. At this level, we're going to keep it pretty simple so we can use this information of delta H and see how it applies to chemical reactions. Down here at the bottom it says usually your delta H and your delta E are pretty similar in value, and that is true, and particularly at the level that we're going to be studying this is going to be true. We could almost interchangeably use delta E and delta H. But then it goes on to say that the difference is largest for reactions that actually produce or use large quantities of gas. Now, why would that be the case? Well, it would be the case because how do you measure gas, or how do you work with gas? Well, gas involves inherently pressure and volumes. So if you have large amounts of pressure and volume, the opportunity for there to be alterations in pressure and volume over the course of a reaction comes into place. And in that way, you could end up having a different delta H than a delta E. But fortunately for us, we're not going to be dealing with large quantities of gas. So when we're talking about delta H, it can be either a positive value or a negative value. Now let's think about what's happening here. What are we talking about when we're talking about delta H? Well, we're talking about the heat that is being released or evolved from a reaction. Now, I use the word evolved very loosely. Just basically, I don't want to say generated. I just want there to be this notation that it's like something that's part of the system. And sometimes it gets absorbed and sometimes it gets released, just like our other reactions. So what happens when delta H is negative? Well, no surprise, that's going to be a reaction where the surroundings actually heat up. This is going to be a scenario where the system is actually losing that heat. It's experiencing a heat deficit, just like your bank account would if you didn't put it, if you took something out of it, it would be a loss. So your system you're experiencing a loss. That loss is going into the surroundings, and we would call that an exothermic reaction. Hey, that's good news. That's something that we've known before, and here we're revisiting it. So that means then if the delta H is positive, in this case, heat is being absorbed by the system from the surroundings, and for the system, the delta H would be expressed with the plus sign, and that means that because heat is going into the system from the surroundings, this would be an endothermic reaction. So a negative delta H means exothermic, and a positive delta H means endothermic. So what's happening at the molecular level when we're involved in exothermic reactions? Well, for an exothermic reaction, the temperature of the surroundings will rise, and that's due to the release of thermal energy by the reactants as they go into the product formation. Now, this extra thermal energy comes as a result of the chemical components rearranging. So what's happening to a molecule when it undergoes a chemical reaction? Well, if it's a molecule going into a reaction as a reactant, those bonds have to be broken, and it gets so your molecule gets broken down into its elemental parts, and then they rearrange, which takes energy. So energy gets released when the bonds get broken. Energy gets absorbed when the bonds get rearranged and made. And if the difference between that breaking and the rejoining is enough to release heat, then you have the exothermic reaction. So that means that you have high energy reactants, low energy products as a result. That type of reaction tends to be driven forward pretty rapidly, because Mother Nature, although she's a drama queen, she has a tendency to be a little lazy, and she likes to have low energy systems. So most reactions will move forward because the net result of bonds being broken and bonds forming creates a system that can exist in a more stable state. Now, sometimes you have to put some energy into things to get them to move forward. That's true. But for the most part, a lot of things will exist in the state that they exist in because it's a more stable. It's more stable energetically and can be lower. We're going to look at systems where that's not necessarily the case, where we're going to have to put energy into rearranging of molecules and elements to make high energy reactants. But sometimes you need high energy reactants because those high energy reactants will then be utilized for something else, and the energy that's within those bonds will get harnessed and used for other systems. So, for example, making butane or propane, formulation of those gases, we bring those things home and we burn them and make low energy products. But them being in their high energy state is something that we can utilize. So it's like this endless circle of things being made and things being broken. I really got off on a tangent there, but it wasn't a bad talk. So in an exothermic reaction, what ends up happening is that by the time the reactants and the products have rearranged, the bonds that were formed have lower energy than the bonds that were broken, and the energy difference gets released in the form of thermal energy, and you feel it as heat. So that is the whole nature of an exothermic reaction. Now, an endothermic reaction is just the opposite. In this case, the reaction will take heat from the surroundings and use that kind of as a reactant itself to drive the formation of the products. So in this scenario, what ends up happening is that you have bonds broken and bonds being formed, and the products of this reaction will have more chemical potential energy than the reactants did. So this is where we're now making higher energy product than we had reactants. And we basically have harnessed some heat energy from the surroundings in those bonds. Now, eventually we'll take that product and we'll do something with it, and we will release that energy and use it for something else. So let's see. To acquire this extra energy, some of the thermal energy of the surroundings is converted into chemical potential energy and stored in the products. Yeah, that's just what I said. So that's it. This is the circle of life. This is the conservation of energy that happens throughout the universe. Stuff gets transferred from low energy to high energy, and then from high energy back into low energy, and nothing ever gets destroyed or made in the process. So now that we have this delta H, this enthalpy, what are we going to do with it? Well, we're going to do some math because this is chemistry. I think chemistry should just be renamed fancy math, but here we are. We're going to do some math with this. So whenever you have a reaction, such as we have here, where we have propane interacting with oxygen to create carbon dioxide and water, this is a combustion reaction. When you have an equation like this, it will have an enthalpy to it. And that enthalpy is very much like a fingerprint. So that you know that if you have this type of reaction, you can predict how much energy is going to be released as a result of this reaction being driven forward, or how much heat will be absorbed as a result of this reaction being driven forward. Now, in the case of this combustion reaction, heat is released. That's why we have a negative delta H there. We have a negative enthalpy. Now, what does that mean to us? Well, that means we're going to be using it in stoichiometry. So what does that mean? Well, let's revisit what stoichiometry means. Stoichiometry is the math that allows us to look at an equation like this and find a relationship between any one of the reactants and anything else in the equation, or any one of the products and anything else in the equation. So for example, we know that 1 mole of propane will require 5 moles of oxygen gas in order to drive this reaction forward. Where did I get that 1 and that 5 from? Well, remember, these have coefficients in the front of them in these equations. And although they're not written in there, we can assume the units of moles here. So 1 mole of propane, 5 moles of oxygen. So we know that it is a 1:5 ratio between propane and oxygen. If we wanted to find a relationship between propane and carbon dioxide, it is a 1:3, oops, I forgot my mole right there, 1:3 ratio between propane and carbon dioxide. And I can do the same thing with propane and water, or, hey, look, propane and enthalpy. Because just like I need each one of these to be exactly as they are for this equation to move forward, I also need the value of the enthalpy to be exactly this as well. So I could say that 1 mole of propane has a relationship with negative 2,044 kilojoules of heat when in this combustion reaction. So yes, we will be doing stoichiometry and we'll be using relationships like this. All right, so let's look at this example 9.7. So we have a propane gas tank on a home barbecue that contains 13.2 kilograms of propane. Oh, what do we know about kilograms? Well, that is a mass measurement in grams, a form of grams called kilograms. And they want us to calculate the heat, which is going to be Q, in kilojoules associated with the combustion of all of the propane in that tank. Well, okay, so we are given a value in kilograms or grams, and they want us to calculate a value in joules. So here we have a mass value, and they want us to come up with a Q value. Can we do that? Oh my gosh, can we do that? I don't know. Can we? Let's just click on the button here and figure out what it says. So we're given kilograms of propane and they want us to find Q. So let's start by getting out of kilograms and into grams by using molar mass. Actually, let me back up. We want to get out of kilograms into grams and then into moles by using molar mass. That's what we want to do. So we want to go kilograms of propane to grams of propane, figure out the molar mass of propane, and get us into moles of propane. Why do I want to be in moles of propane? Because I have a relationship in this equation right up here that says for every 1 mole of propane that I burn, I evolve negative 2,044 kilojoules of heat. That's why. So this is the value that we're ultimately going to plug in our equation, and this value comes from our equation. Stoichiometry. So these are our relationships that we're going to use, and if we plug this in, we're going to start with the value that we're given, which is our mass. We're going to get it out of kilograms and into grams. And then we're going to get it out of grams and into moles by using molar mass of propane. And now that we're in moles of propane, we don't want to be in moles of propane. We want to be in kilojoules. And we know that for every 1 mole of propane, we will evolve a negative 2,044 kilojoules. And we got this value from our equation. And in this way, we can figure out what the kilojoules of heat will be released. It's a negative value. That means it's going to be released as a result of burning the entirety of what's in that propane tank. Now, a nice, easy experiment that we do in lab, or would have done in lab, is using the coffee cup calorimeter. And a coffee cup calorimeter is a wonderful little device because it allows us to put all of these things that we've been studying as far as heat evolution and endothermic, exothermic reactions, we get to put them through the test. And all it takes is a little bit of styrofoam and a thermometer and a sister and some pretty basic stuff that I can pull together in the lab. And it's the same thing that we've talked about earlier in the lecture, where we can figure out how much heat gets released and how much heat gets absorbed. So in a coffee cup calorimeter, what ends up happening is that you would have some water in your coffee cup, and you would put something in there that would undergo some sort of a reaction or something that would be hot, and you would let it warm up, and you would take the readings on the thermometer, and then when the thermometer stopped moving, you would know that you had your final endpoint, and then you can do the calculations using the mass of whatever was in there plus the specific heat of either the water or the stuff that you used, and then the temperature change that the water underwent. So it's a really nice experiment to do. And you've got two systems. You've got the system of the stuff that's undergoing the reaction. So say that we heated up a penny and we put it in our coffee cup calorimeter. Well, the penny would cool. It would go from a high temperature to a low temperature, and the water in our coffee cup would go from a low temperature and it would nudge up to a higher temperature. So in this case, we could figure out the Q of the reaction of the penny and what the water experienced as a result of that. So this is just a nice way for us to be able to work with those concepts and plug in some values from our own data points. I'm really sorry we don't get to do this one because this is so easy to do, and it's actually kind of fun. Now, earlier in the chapter, we talked about state functions. And remember, a state function only looks at the initial value and the ending value in a system, and it doesn't take into consideration the process of how we got from and to our values. Well, Hess's law allows us to actually take a peek at the various steps required in a chemical reaction, because even though we write a simple chemical reaction where we have reactants and it delivers products, sometimes those steps are not always that straightforward. Sometimes you have to create a couple of intermediary steps in order to get to that product. And Hess's law allows for us to examine those intermediate steps and figure out some information about the reaction. So let's see what we have here. So for example, when a reaction, and there's rules regarding Hess's law. So Hess's law basically allows us to look at multiple steps of a reaction and create some relationship between them. And there are some rules that Hess has come up with. They're basic mathematical rules that apply to chemical equations. So for example, when a reaction is being multiplied by a factor, let's say we're going to multiply a reaction by 2. For some reason, we need to double everything in a reaction. Then the delta H of that reaction is also multiplied by that factor in this case too. So for example, we have carbon and oxygen creating carbon dioxide, and this is the delta H for that reaction. If for some reason we needed to multiply this by 2, not only would we multiply all the products and reactants by 2, but we would also double the delta H, because remember, delta H is going to be, it is a physical property and it depends upon how much stuff you have. And in this case up here we're dealing with only like a 1:1:1 mole ratio, and here we're dealing with we've doubled it, so it would make sense that the heat would also be doubled. Here's another rule according to Hess's law regarding reactions, is that if a reaction gets reversed, then the sign of the delta H is also reversed. So look here. So if we put carbon dioxide as a reactant, where up here it is a product, then what ends up happening with our delta H is the sign gets reversed. Up here it is a negative, and down here it becomes a positive. Yeah. So why do we really even need to know these rules? Well, here's the reason why, is that if we started off with a substance that started off with products A and B, and it had to go through a reaction to create this product C, and then C had to go through a reaction that went this way to create product D, if we just looked at this as our starting point and this as our end point, we wouldn't be getting a real true value of what it took to create this product D. But when we take into consideration this first reaction, this first delta H, and then this second delta H, that allows us to have an understanding of what actually happened here, and be able to calculate a third delta H. And in order to come up with these, this system right here, we have to be able to sometimes manipulate reactions in order to do that. So let's actually put this to work so you understand what I'm talking about. So let's put Hess's law to work. And we're going to do it by this equation right here. So we are being asked to find the delta H for this reaction where we take carbon and hydrogen and create propane. Now you can't set carbon and hydrogen in a room together and hope that they form propane. You actually have to go through a little bit of a process. And there's 3 equations that will kind of get us there, and here they are right down here. Now each one of these reactions has its own enthalpy, delta H. And are we going to be able to use these 3 equations and their delta H's to figure out what is happening with our final reactions, delta H? Why, indeed we are. And I will show you how we're going to do that. So let's just start. So the first thing we're going to do is we're going to look at this reaction right here, this very first reaction. And we want to find products and reactants that are in our final reaction. And we want to make sure that they are on the same side of the transformation arrow as the product or reactants in our final reaction. So let's see. We have propane and we have propane. Now in our reaction here, propane is a reactant, but in our final reaction, it's a product. So we're going to have to reverse this first reaction to get this propane on the right side of the transformation arrow. Now, we don't have oxygen in our final equation, nor do we have carbon dioxide or water. We're not going to worry about those for now. The one that we are concerned about is this propane. So we're going to reverse this reaction. And when we reverse this reaction, which means we're going to use carbon dioxide and water as our reactants and propane and oxygen as our products, what are we going to do with our delta H? We're going to have to change it from a positive to a negative, or in this case, a negative to a positive. So let's do that. So we can see that what we've done here is we've taken our carbon dioxide and our hydrogen, and water, and we've reversed the reaction and we put our propane and consequently the oxygen on as products, because that is what matches our final reaction up at the top. And you can see that we have reversed the value of our delta H as well. Okay, so far so good. Let's look at this second one. Now we have carbon. Oh, look, we have carbon right here, and they're both reactants. That's good. There is no oxygen in our final reaction, nor is there CO2. We're not going to worry about that. Well, this is great that carbon's already a reactant, but what do we notice here? Well, here we have only one carbon, and how many do we have here? Yeah, we got 3 in our final reaction. So what we're going to have to do with this reaction is we're going to have to multiply it by 3. So if we multiply everything in this reaction by 3, what are we going to have to do with delta H? We have to multiply it by 3 too. So we take our reaction, multiply it by 3, multiply our delta H by 3 as well. Okay, so the third reaction, we're going to have to multiply by 2. So we're going to do that with this reaction. And now we can take all of these values. So we tripled our carbon dioxide. No, we took our first reaction and reversed it. We tripled our second reaction, and we doubled our third reaction. Now we're going to add up everything that is on the reactant side and everything that's on the product side, but we're going to get rid of repeating terms first. So we're going to get rid of anything that occurs both on the left of the transformation arrow and on the right of the transformation arrow, which means that here we have 3 carbon dioxides, and we happen to have 3 right here, so they're going to go away. Here we have 4 waters, and down here we have 4 waters, so they're going to go away. What about this oxygen? We got 3 right here, and we got another 2. That means 5 oxygens are right here. We've got 5 right there. So all of these go away. All of this goes away. What we are left with is 3 carbons, 4 hydrogen molecules, and 1 propane, which is our final equation that we were given at the very beginning. Now what's important is what's happening over here, because with all the flipping around and multiplying of our delta H's, if we add all of these together, that will give us the delta H of the reaction. And in this case, the delta H of the reaction ends up being a negative 105 kilojoules. So that's how you use Hess's law with these 3 reactions. So earlier in the lecture, when I was talking about endothermic and exothermic reactions from the particulate or the molecular view, I talked about how bonds were being broken and how bonds were being made in order for reactions to be driven forward. And when we're talking about that, we're looking at what are called bond energies. And these are the chemical reactions that involve the breaking of reactant molecule bonds and the making of new bonds to form products. And bond energies, let's see, what can I say about these to be concise? Basically, bond energies are going to be chart usage. You don't know inherently what a bond energy is. You don't know what it is. You have to look it up on a chart. But how are we going to use bond energies to do calculations? Well, let's take a look at another slide and see if we can figure that out. So when we're looking at bond energies, before we actually look at breaking and reassembling bonds, what we need to keep in mind is that when we're looking at the delta H of a reaction, it's going to mean that we've taken all of the delta H's of the bonds that were broken, all of the bonds that are broken, and we're going to add all of the bonds that are formed. Now, why would we be adding? Well, we're going to be adding because one of these is going to be a negative delta H, and one of these is going to be a positive delta H. So the breaking of bonds is the releasing of is the input of energy, the input of energy to break the bonds. And so that delta H will have a positive value. And the making is exothermic by nature. So the making of the delta H bonds, the bonds being formed, will have a negative value. So that's why we say plus here in our final equation, because the bonds broken might have a positive value. I mean, it will have a positive value. The bonds formed will have a negative value. Sometimes this is larger than our value of bonds formed, in which case we would be dealing with an endothermic reaction. Yep. And sometimes the opposite is true, in which case we would be dealing with an exothermic reaction. So let's take a look. So before we actually take a look, let's look at some trends in bond energies. I thought we were going to hop right into working one, but I forgot I left the slide in here. So if we look at the values, and these values come from charts, we can see that starting with just a simple carbon-carbon bond, 347 kilojoules. But if we double the bond, that's actually a shorter bond. And look, it takes a lot more energy to break up a double bond, and then it takes even more to break up a triple bond. And even if we were looking at a bond between carbon and nitrogen, we can see that we are almost double, going from single bond to triple bond, and then we're like 1.5 times as strong again, going from single to triple. So double, from single to double, it doubles, and then going from double to triple, it does a little bit less than double. Let's see, if in general the shorter the covalent bond, the stronger the bond, the shorter the bond, the stronger the bond, no surprise there. And we can see these three have are similar type of bonds. The values coming in pretty close to each other as a result of that. These are all halogens. Halogens are basically constructed the same. But you can also see that bonds get a little bit weaker going down a column, and the bonds get stronger going across a period. So I really just want you to know how to use the chart and figure out the bond energies. So here's the chart that you'll use when you're doing the calculations. So say like you had something that had 2 hydrogen-carbon bonds, like you had a carbon that was bonded to 2 hydrogens. Well, you would come to the chart and you would say, oh, well, the value of that carbon-hydrogen bond is 414, and I got 2 of them, so I've got to multiply 414 by 2, and that would give you the bond energy for each one of those carbon-hydrogen bonds. So that's how you would use this chart. It's just that simple. All right, so let's take a look at this. So let's say that we started off with some methane, that's CH4, and a couple of chlorines. So in order to get this thing to break apart, what we would have to do is we would have to break apart the 4 hydrogens from the carbon. So we'd have to break up the 4 carbon-hydrogen bonds, and we'd also have to break up the 2 chlorine bonds. So that would be all of that breaking up going into one portion of your delta H. That would be the delta H breaking apart part. And then when we start reassembling everything, the thing that we're going to create is we're going to create a carbon-chlorine bond and a hydrogen-chlorine bond. So we would have to reassemble the molecule. So we would reassemble 3 carbon-hydrogen bonds and then 1 carbon-chlorine bond, and then we would also reassemble a hydrogen-chlorine bond. Now, the way I just explained this is that I would say disassemble everything and then reassemble everything. And I know some of you, because I know how students are, you're thinking, well, geez, we had to reassemble 3 of the carbon hydrogens over here, so why do we need to break them apart over here? Well, you really don't. I mean, you don't have to break them apart. I just do that to keep everything really clean. If you're good and you can kind of do that, which is actually what the author has demonstrated up here, he's only plucked off 1 hydrogen, so he broke that 1 hydrogen-carbon bond, but he broke both of the chlorine bonds, and then he rearranged and did the assembling of them that way. You could do that. In class, I tend to break down everything because I want you to understand that things have to be broken. to be built back up. But yeah, certainly you can take that shorthand and just break down exactly what you need to, as the author did in this example. Because the math ends up working, right? Repeating values, they cancel. So let's look at this example here. So we have methane gas and a couple of water molecules, and then we're going to create some hydrogen and some hydrogen gas and some carbon dioxide. Well, in this scenario, we are going to have to break down all of the molecules to build the molecules. So we will be calculating all the bond energies for the two reactants and all of the bond energies for the two products. So we've drawn out the structures, the formula structures, so that we can see that we have a carbon-hydrogen bond here, that's one, and then a second one here, third one, and a fourth one. And because we have two of these, we're actually going to have 4 hydrogen-oxygen bonds, because there's one here, and then there's another one here, that's 2, and then we're going to multiply it by 2. And we're going to have 4 of these hydrogen-hydrogen bonds, and then we've got 2 double bonds carbon-oxygen. So if we go back to the chart and we plug in the values, it would look like this. Because we have 4 of these carbon hydrogens, we would take 4 times the carbon hydrogen bond. We have 4 of these OH bonds, and these values are coming directly from that chart from your book. So our delta H for breaking up the bonds is going to be equal to 3512 kilojoules. Hi, kitty. I don't know if you guys just heard that, but that was my cat. I don't know how she feels about bond energies. I know, kitten. Okay. All right, so what happens with the product side of this? We're going to do the same thing. So we would take the 4 HH bonds and the 2 carbon-oxygen bonds, go to the chart, find what their values are, and those are going to be negative values, so it ends up being a negative 3342 kilojoules. And then we put all that together in an equation, and we end up seeing that the delta H for this reaction is 1.7 times 10 to the negative 2 kilojoules. Math is not hard. You just have to have an understanding of what you're doing with your molecules and make sure you draw your molecules correctly. So your book goes into something known as standard conditions and standard enthalpy formation. And when you're talking about standard anything, whether it's standard temperature and pressure, standard heat, standard enthalpy, basically what that's saying is that it is a state defined with a certain set of conditions. And in the case of standard state for enthalpy, you're dealing with a pure gas at exactly 1 atmosphere of temperature, a pure solid or liquid in its most stable form at exactly 1 atmosphere of pressure, and a temperature of interest, which is usually 25 degrees Celsius. And that the substance in a solution comes in at a concentration of 1 molarity. So because these conditions can vary, scientists like to create this ideal situation where things come in at these certain values, because then it allows them to isolate some other characteristics of the situation or the condition that they can, and it allows them to study that. So what do we do with standard conditions and standard enthalpy of formation? This is chart usage. This is complete chart usage. So what does that mean? Well, let's just take a look. So this is a table that's in your book, and you would, for example, have an equation given to you that may involve something like methane. Methane comes in right here, and it would give you the value of the heat of formation. Or maybe you're coming in with something like water. Water in the gas form has a certain heat of formation, and versus water that's in the liquid form comes in with a certain heat of formation and a certain enthalpy. So you will come in and you will just extract these values and plug them into your equations, your chemical equations for the creation of your products. So that's how this works, and it's just that straightforward. So let's take a look. Okay, so this problem, example 911, is asking us to write balanced equations for the formation of these two compounds and include their enthalpy at standard their standard enthalpy as standard conditions. So what would we do? Well, we would take this magnesium carbonate, which is this first one. And what we need to do in order to write that equation is that we would spell out magnesium solid, carbon solid, oxygen gas, and then we would write our formula over here. Now, in order to create a balanced equation, we've got a little issue because we have 3 oxygens right here, we have 2 right there. Now, to balance this, what we would end up having to do is put a fractional coefficient right here. So we would put that 3/2. And normally what we would do is then multiply everything by 2, which means we would have 2 magnesiums, 2 carbons, 3 O2s, and 2 magnesium carbonates. But when we are dealing with enthalpy, our enthalpy value is going to be coming in at kilojoules per mole. So when we're looking at the formation of our product, this is our formation of our product. We need to make sure that what we have is 1 mole of our product. So in this case, we're going to leave that fractional coefficient because by leaving it there, we have 1 mole of our product. Now, where did I get this number right here, this negative 1095.8 kilojoules per mole? There's a chart in the book. It's in Appendix 2. And you look up magnesium carbonate and you pull the value off and you plug it in. Chart usage. Hardest thing about this is writing the balanced equation. And we've already had that done. We've already worked through this stuff. All right, let's look at the creation of glucose, which is C6H12O6. So in this case, we would write out carbon and hydrogen gas and oxygen gas, and we end up with C6H12O6. Well, we can already see we're going to have an issue because we're going to have to multiply everything by 6 over here, right? We're going to have 6 and some other stuff. So balancing the equation is probably going to be the most difficult thing that we deal with. I don't think it's really going to be that hard with this one. Let's go to the next slide and see. So we're going to need 6 carbons, 6 hydrogens, and 3 oxygens, and then we're balanced. Oh, and where did I get this number? This number right here? I just pulled it off the chart in the back of the book. There you are. Example 911, not that hard. So just like with other equations where it might not necessarily be, here's your equation and you start with this and you end with that and then there you're done. It's entirely possible that we could have a scenario using our standard enthalpy and have 3 equations that are going to get us to our final equation. And when that's the case, we handle it just like we did with Hess's law and pulling the values off the chart. So nothing new here. It's just that instead of calculating the numbers, we get to do a little bit of chart usage. So let's see what we mean by that. So look at this. So we have methane and oxygen undergoing a reaction creating carbon dioxide and water. And we're going to have a couple of equations that get us there. So if we look at what we have here, we're starting off with our reactants right here. And we're going to end up with our products down here. So we have high energy reactants, low energy products. And what happens in between is that we have basically the breakdown of our elements into their constituent elements. If you go to the chart and you look up methane, methane comes in with a value of a positive 74.6 kilojoules. Oxygen comes in with a value of 0. So to get from here to there, it's going to be this positive 74.6. Now, if you go look it up in the back of the book, it's going to be a negative value. And the negative value means that you are creating methane. It's for the creation of methane. But in this first step, we're not creating methane, we're undoing methane. So it's going to be the opposite of the H final in the back of the book. So instead of a negative 74.6, it'll be a positive 74.6. So that's the first delta H that we're dealing with. Then the next thing that we're going to do is we're going to have to create carbon dioxide. You go in the back of the book and you look up the value for that. And that's going to be one of our low energy products. And then we're going to create water. And that's going to be the other low energy product. And if we take and you have to do a balanced equation for all of this sort of stuff. These are the 3 equations that are going to come into play here. Then you would add all of these up just like we did with Hess's law, these delta H's, and come up with the delta H for the reaction. Now this looks a little confusing. I get that it looks a little confusing, but if we look at each one of these steps and we see what we have going on here, in order to create methane, it's going to take using carbon and 2 hydrogen gases. That's the reaction that would have been given to us before, and we're having to create it here. So in order to do this, the creation of this, here's our delta H for the creation of methane. And then to create carbon dioxide, which is this step right here, we're going to need carbon and oxygen. And the delta H for creating carbon comes in at a -393.5, again pulled from the chart in the back of the book. And then to create water, we're going to have to take hydrogen gas and water molecule, half of a water molecule, and find its delta H at standard temperature, pressure, and get its value. So where before in the problems that you did, you were given these 3 equations, you would have to create them here. So because each one of these needs to be created, the methane needs to be created, the CO2 needs to be created, and the H2O needs to be created. And so that's what each one of these is allowing for, is the creation of that. So this is the thing that you didn't have to do before. What does this mean to you on an exam? On an exam, I will give you these. You won't have to go through the creation of them. What is entirely possible is that you might not be given the delta H. You might have to look it up on a chart. Using a chart's not that hard. So, but anyway, that's why this is confusing and why I wanted to go over this, because I know this is included in the book, and I wanted to add that clarification. So now what we do is what we've done previously is we rearrange everything. So where before we had the CH4 on the left, no, the right of the transformation arrow, we've moved it to the left, which is where it is in our equation up here at the top, and we've reversed the delta H. And our CO2 is on the right side of the equation, and our H2O is on the right side, so we keep those. Add these 3 up, and there is our delta H for the reaction. Just what we did before with Hess's law. So this slide takes the same information that was on the previous slide, but it puts it in the format that we were introduced when we were first introduced to the standard enthalpy, taking the enthalpy of the bonds made and subtracting or adding the negative of the bonds that were broken and coming up with our value that way. So it's the same information as before. It's just that it's now taking it and putting it in the format in which the formula was introduced to us. We were introduced.